Okay, let's come up with the rational function that would produce this graph. So in looking at this, we're going to collect some information, x-intercepts, vertical asymptotes, horizontal asymptote, and y-intercept, and just put all this information together into a function. So the first thing let's look for are x-intercepts. Now we don't have many on this graph. It looks like we cross the x-axis here at, I'm going to go ahead and say that's an x-intercept at 3. Where that contributes to our function is that goes with a factor x minus whatever we set our x-intercept or 0 is, goes in the numerator. It's always x minus whatever we list as our x-intercept, or 0 or root. Okay. The next thing I want to look at is it appears that at this x-intercept we cross the x-axis. This contributes to the multiplicity on this factor. All right, by multiplicity, we mean what exponent that factor is raised to. Whenever we have a cross, that's going to mean an odd multiplicity. If it were to touch and come back the same direction, stay on the same side of the x-axis, we would say that's a touch and it would be an even multiplicity. But this one was a cross, so it's going to be an odd multiplicity. We tend to simply go with the smallest odd number possible, so I'm going to say that's raised to the first power. Next, vertical asymptotes. These are these vertical dashed lines you can visualize on our graph in red. Looks like we have one at x equals -3. And a second one at x equals +4 on the right-hand side. Now, when I'm looking at these, they contribute to factors in our denominator. So again, it's the same premise. It's always x minus whatever that x value is. So x minus -3 is x plus 3. And x minus 4 is going to be a separate factor. Okay. The next thing I want to look at is, do we stay on the same side of the x-axis or do we go to opposite sides of the x-axis? Sort of the same question as this cross for our x-intercepts. So looking at our vertical asymptote here at -3, one tail goes down and the other tail goes up. So I would say these are on opposite sides. And very similarly over here at 4, we have one tail goes down, and on the other side as we get close, the other tail goes up. So again, that's on opposite sides. What that tells us is very similarly about a multiplicity or a power on those factors that we got from these two values of x. All right, when we're on opposite sides, much like when we cross the x-axis, this is going to indicate an odd multiplicity. So since both of these went to the opposite sides, both of these are going to get odd multiplicities. Again, I'm going to raise these both to the first power, going with the smallest odd power, as opposed to 3 or 5. Okay. Horizontal asymptote. It's a little bit tough to tell from our graph here, but it appears that our graph is continuing to go down and we don't have any other x-intercepts here. So I think what's happening is we're getting closer to the y equals 0 or the x-axis. Same thing over on the left-hand side as we track this out forever. It appears to get closer and closer to the x-axis. We don't see any more x-intercepts, so we can't assume that it crosses the x-axis anywhere out here. Okay, how we get this is we compare degrees of numerator and denominator. So this is an indication that the degree of the denominator is bigger than the degree of the numerator, which kind of makes sense as we kind of compare these degrees. If we were to multiply out our numerator, we have just x to the first power, degree 1. If you multiply out our denominator, we have x squared, or degree 2. That indicates that the denominator's degree is bigger than the numerator's degree. So we already fit into this situation. The last piece of information we want to collect is the y-intercept. Hopefully not too bad to collect this. Appears it's going to be a 0, 1 for our graph. How that's going to contribute is, with our function, we're almost done. However, you may have some sort of scalar multiple, meaning some constant sitting out here in front. Could be a stretch, could be a compression, could be a reflection that would contribute to changing our graph around. We're going to find this value for a, just some number, by using our y-intercept. So to use it, I'm going to say x value, f of x value. Let's plug the 0 in for x and plug the 1 in for f of x. So 1 goes in for f of x. We have a multiplied by 0 minus 3 over 0 plus 3 times 0 minus 4. Now with an equation that only has constants in it except for a, let's do a little bit of work and solve down for a. So some simplifying first, we can say negative 3a in our numerator over, that's 3 times negative 4, or negative 12. I'll simplify just a little bit first within that fraction on the right-hand side. These are both negatives, so they can cancel out and make a positive. And these are both multiples of 3. So I can say this is equivalent to a over 4. So to get a by itself, I'm going to multiply both sides by 4. So we end up with a equals 4. The very last thing we need to do is take this value back up to our equation at the top and plug it in for this function. So we can say our end result here, the function is going to be 4 multiplied by the quantity x minus 3 over the quantity x plus 3 times x minus 4. And that's going to be the function that we were looking for that would produce exactly this graph that we started with. All right, I hope this helps out. Hopefully it makes sense one step at a time as we go through this, as you're trying to find functions that resemble the graph that's given for rationals. All right, good luck.